So now it looks. Dr.
Let's
Prajapati,
see.
hello.
Yes, I have done. You can continue.
You see my screen now?
Yeah, Ronnie, you can continue.
Yeah,
Okay.
now your screen is there. Yeah.
Okay, you can see my screen and you can hear me, right?
Yeah, yeah, I can hear.
Okay, good. Okay, so I'd like to thank the organizers for giving me the opportunity to talk. I wish you all well in these difficult times. I mean, we are here in lockdown and I'm doing this from home, like I guess you all are doing the same. So what I'm gonna use these 20 minutes or so for is to tell you about a fresh look at waves in ion electron plasmas. And I'm calling this reformulating the textbook treatments. And this is part of some effort that is European funded, and hence all these logos. You can ignore those. So if I want to reformulate textbook treatments, I should probably at least remind you a little bit of what is the textbook treatment that I'm referring to. And I hope that this particular part will be very familiar to those that are actually teaching plasma physics to students, because you find it in almost all the textbooks. So I'm going to talk about ion electron plasmas, okay? And in ion electron plasmas, we then basically have the following. To start discussing the waves in a uniform medium. So we start from the Maxwell's equations. These are basically the Maxwell's equations. And we are going to assume for a plane wave with a wave vector that I indicated with the boldface vector k and with frequency omega, we are going to use this plane wave decomposition in the Maxwell's equation. And that's not very difficult to do. You basically directly combine these because all your derivatives become simple algebraic factors. And you have already an equation that links the wave vector with the frequency and the perturbed electric field, E, and also the perturbed current, J. Now, if you now would be able to write the perturbed current in a direct proportion to the perturbed electric field, then you will be in business, because you would have a 3x3 formulation with a 3x3 matrix operating on the perturbed electric field. So what we're doing is we're supposing that the current is proportional to the electric field, introducing the conductivity tensor, or introducing in an analogous way the dielectric tensor, which is related to that conductivity tensor, but it also involves the frequency itself. Then, if we have this proportionality, using this dielectric tensor, we actually have what we want. We have an equation that basically operates on the perturbed electric field and is formulated in a 3x3 system. And so for the solutions to be found, we want to have basically that the determinant of that 3x3 system is basically equal to 0, so that we have a non-trivial solution. And that is the dispersion relation for waves in an ion electron plasma. I should perhaps stress that I'm going to talk quickly about a cold ion electron plasma. So the only thing that I haven't yet explained is how to get this dielectric tensor, right? How to express the current in terms of the electric field, but also that is not so difficult. So here I specify to a cold plasma. I have my species, these are electrons and ions on the other hand. So I just take my equation of motion, the Lorentz force here, and I do the same thing, I linearize, and you can appreciate from this equation that what you get if you linearize this, you can directly express your perturbed velocity in terms of your perturbed electric fields. Hence, if you then sum all the contributions to get the current, you basically can get the components, and that's basically what is done in textbooks. And the final result is that that 3x3 matrix, basically the determinant of it, can be written in this form, where I now normalize my wave numbers with the skin depth, delta, which is light speed divided by the plasma frequency. I also normalize my frequencies to the plasma frequency. And I have basically one angle. I have a background magnetic field, And I remind you that we have a wave, a plane wave with a wave vector k. So there is an angle between those two. And that is basically incorporated in this lambda, basically the cosine square. So this is it. We have the dispersion relation. So this dispersion relation, actually this A, B, and C, I didn't give you them explicitly, but they are three third order polynomials omega squared. There are actually two parameters only in the cold ion electron case, which are essentially the normalized ion and electron cyclotron frequency. So the electron cyclotron frequency and the ion cyclotron frequency are the only parameters. Now, to be honest, I already rewrote a little bit what you find in the textbooks to get this form, because I said that the A, B, and C are actually polynomials. If you go to any textbook, you'll find this written in a slightly different way. Namely, you will find factors like 1 over omega plus or minus E plus over everywhere. So it's actually written in terms of rational expressions. And that's because the textbooks prefer to work with the refractive index. The refractive index, n squared, being basically the wave number divided by the frequency. So if you look at this expression, you can see that here you have k fourth, here you have k squared omega squared, here you have omega fourth. So if you divide by omega fourth, then you have directly a quadratic expression in n squared. Everybody can solve that. So this is just a formal solution. It's a quadratic dispersion relation. It has two roots. And so the biggest one we'll call the fast, the slowest one we call the slow. They have then another categorization that comes in from the limits parallel to perpendicular. And we have the right or left polarized electromagnetic waves and also O and X modes. That is in a nutshell what you find in a textbook. Another thing that you may find in textbooks, for instance here, this is from Blanford and Thorne, are the celebrated Klemov-Mullally-Alice diagrams where this whole information is in this complex figure here, where we have refractive index horizontally, magnetic field vertically, and then by necessarily the frequency sort of runs through this thing. Main point is, if you have ever seen these diagrams, you know that you're never using them really in practice. If you never used them before, you can forget about them, because that's what I'm going to tell you. I'm going to take a fresh look at waves in ion-electron mixtures. So before I do that, I come from magnetohydrodynamics, and so we have written an interesting book, I hope, about it. And so everybody knows that if you're in a uniform medium and you treat it with a magnetohydrodynamics, you have slow alphane and fast wave pairs, but also an entropy wave. So you have essentially 7 waves. Now the phase speed diagram quantifies basically how for every angle between the wave vector and the magnetic field, how far a plane wave can travel in a fixed time. And the group speed diagram is giving you information on the energy flow. It's basically telling you how the constructive interference of all plane waves happens. And so these are basically the so-called Friedrichs diagrams. This is the phase speed diagram. This is the group speed diagram. And so the main point in Mhd is that all of the waves are anisotropic. So you have to show in this one view here, if I focus on the left, how horizontally the magnetic field is basically horizontal always in these plots. But if you look at the plane wave that travels at an angle, then if you vary this angle, the reach of that wave will differ. And so that is then for the slow, I will use green for that, alphane, I will use red for that, and fast, I will use blue for that. And the group speed diagram, by doing Huygens construction on the left one, you get this one. So that's what we know from Mhd. How is this embedded in two fluid and in the things that we do not find in textbooks? Well, let me go to the two fluid equations. These are the two fluid equations. We have conservation of mass, momentum, and energy for the electrons, the same for the ions, and of course we have the full set of Maxwell's equations. Now let us count how many waves do we expect? Well, how many waves are, of course, how many times we find the partial derivative with respect to time. So we have 5 here from the electrons, 5 from the ions, and then we have another 6 here from the Maxwell's equations. That is 16. But we have 2 constraints from the Maxwell's equations, just like telling you how the divergences behave. So we have actually 14 waves that actually are described. And in this expression, we also allowed for collisions. I'm going to assume that they are 0 in the following. So I'm going to treat an ideal plasma. And the cold limit would just be where these pressure terms are basically 0. So if you take the fluid equations, you expect 14 waves. Now, those 14 actually have also 2 trivial entropy waves that are just there, and they correspond to things that will be advected with the flow velocity if there would be one. So there are 12 non-trivial waves. And it is possible to, from the system that I showed you just the previous slide, to get to the overall dispersion relation as a 12th order polynomial, 6th order in omega squared, 4th order in k squared, for all the waves in an ion electron plasmas. In reality, there will be 4 parameters: the electron cyclotron frequency, the charge to mass ratio, and then the 2 sound speed, which of course would be 0 if we were to treat the cold case. But there are always 4 parameters in this system. And so mathematically speaking, this is basically what we get. We get something that is 6th order in omega squared, that can be 4th order in k squared. And the point is that if we take the cold limit, then indeed the terms going like k to the 6th or k to the 8th basically have coefficients that vanish. And so then we actually recover omega squared times the previous dispersion relation that you find in textbooks if I put it on the same denominator. So this is then the dispersion relation. Now, once you have a polynomial relation, you just call whatever software you like to plot the zeros of it. And here is, for instance, 2 cases where I have the only thing that differs the left from the right is the angle between the wave vector and the magnetic field. And so you will see 6 waves, always like a green one, a red one, a blue one, and then a cyan, a purple, and a black. And so these are the electromagnetic waves. Here in this bottom left corner, you'll find the non-dispersive variants of the Mhd waves. And so you see how if we change the angle, some of these curves actually suddenly show crossings, avoided crossings. So if we now look at the cold fluid regime, right? In the cold fluid case, this was a dispersion relation for a non-cold case because I also have this green curve here, which are the slow magnetohydrodynamic waves. Then I just want to pause here and look again, where are we? In all the textbooks on plasma physics, in a cold ion electron plasma, they talk about 2 waves. They are categorized as slow and fast. They have labels left or right polarized, O or X, coming from the parallel or perpendicular orientation, and formulated as a 3x3 matrix operating on the perturbed electric field. In the fresh look, I tell you there should be 6 wave pairs. Those include the slow, alphane, and fast Mhd wave pairs. And they include the electromagnetic waves and also sort of the counterpart of the Langmuir wave. This is a 6x6 matrix formulation. So we seem to have a problem. Well, we don't really have a problem because if you take the general approach, then I told you the cold limit basically has the slow Mhd waves at marginal frequency and then leaves the dispersion relation that you find in textbooks. So the confusion is slow Mhd waves are not the slow ones that you are talked about in the textbooks. Also, the fast label that is used in the textbook has nothing to do with the fast Mhd. And I can tell you, if you do Mhd and then you start reading this, this is very confusing. The confusion is complete, basically because when you look at this dispersion relation, you can look at it at fixed frequency, and then indeed you have at fixed frequency 2 n² outcomes. But what I like to do is I like to look at fixed wave numbers. And then I have, for the cold case, where one of my frequencies is the 0 slow, I have 5 pairs of omega squared. So if you want to read more about it, there's a paper that I can refer you to. I think this is recorded, so you can probably look at it later. This is the cold ion electron case. There are unique labels that I introduce for these waves because they are ordered. at all oblique angles, frequencies, slow, alphane, fast, modified electrostatic, O and X are ordered, and they can handle the special cases of parallel and perpendicular. The left and right label turns out to be very confusing because that mixes the forward and backward wave pairs. I can show you that. I don't have time to go into details here, but it is a simple mathematical exercise to show that. And what I like to show is that the best way to look at waves in ion-electron plasma is to just accept that in a cold ion-electron plasma, there are only 5 waves, the A, F, M, O, and X, and I can show you phase and group diagrams. Besides the Mhd modes, alphane and fast, the slow does not propagate under cold conditions because the pressure is 0. We have a modified electrostatic mode, that's why I call it the M, and the electromagnetic O and X modes. I take those labels because those were the ones used typically in the textbook, although in the textbooks you should realize that what they call the extraordinary mode is actually a confusing container of 3 modes. So in this unique labeling scheme, I can show you the diagrams, dispersion diagrams. And so I'm going to show you the movie. I hope this works. So I hope you can see my movie here. What I'm going to show you is the dispersion diagram. So omega versus horizontally K. And I'm going to start varying the angle between the wave vector and the magnetic field. And so in the cold case, I have 5 curves, the red, the blue, and these 3 here. And I'm going to start varying the angle here if I play the movie. And what I'm showing in the inset is what happens here, basically, where we had 2 modes that were crossing at exactly parallel, but at any non-parallel orientation, they actually avoid crossing. And so then you always have, if you go from bottom to top of this thing, the ordering between you first encounter the red, then the blue, then the purple, then the cyan, then black. And that's an ordering scheme that you can use at all angles. And so here we are now going to perpendicular orientation, where of course the alphane wave disappears because it doesn't travel perpendicular to the magnetic field. So that is showing you the omega K diagrams at varying angle theta. Now I can do the same information in a phase diagram, where at a fixed K, so now I'm fixing wave number, and I'm showing you the 6 waves in their overall variation with respect to a horizontal magnetic field. So here, for instance, these are the 3 fastest traveling guys, the M, O, and X modes. And I'm going to play this movie because what is hidden here is I'm now changing the wave number, okay? So I'm increasing the wave number, so I'm going to slower, to shorter and shorter wavelengths. And this dashed circle is actually the light curve, the light circle. And we have here a fascinating view on the fact that there are always, in this view, there are always 5 nested phase speed diagrams. And you see that in the limits, they actually behave like Mhd or light waves. These are just light waves at that limit. Now, those are the phase diagrams. Now, a more relevant thing is perhaps group diagrams, because the group diagrams, they give you information about how these 5 waves behave anisotropically and how they basically, handle energy propagation. And that is even more fascinating. I can show you again. Now, of course, because we're talking about group speeds, all the 5 diagrams that you will always see here are actually within the light circle. For the phase speed diagram, that was not necessary, but here it will always be within the light circle. And I'm going to play this a little bit faster here. So I hope you are seeing this. So again, what I'm varying is the wave number or the wavelength. I'm going from the long wavelength limit to the short wavelength limit. And the color scheme are the 5 modes. So the slow is not there, the alphane, the fast, the M, the O, and the X modes. And the point is that you will see some of these waves transform quite dramatically. Okay, so here again, you will see one of these wave transformations. that is particularly intriguing, and it's telling us how all of the waves in an ion electron plasma are particularly sensitive to the orientation of the magnetic field. Here you see how the blue, and I think they interchange, okay? And now basically, let's go for it. So I'm going to play this even faster because I think I'm running out of time. So here again, these are fascinating diagrams. They tell us about physics that is going on in terms of anisotropic wave propagation in cold ion electron plasmas. And what we can do is we can analytically link the long and the short wavelength limits in a way that was never done before. So with that, I'm conclude. I'd like to stress as a take home, the textbook physics on cold ion electron plasmas is of course not wrong. I'm not saying that it's wrong. It's just the way it's presented is very confusing and it's unduly complex. I suggest we should replace it by a unique labeling scheme that works for all angles, namely SAF-MOX. The case of a pair plasma is actually also completely treated, and we have written 2 papers now for the cold and for the warm pair, where again the advantage of this labeling scheme was made clear. For the warm ion electron case, that is actually currently the topic of a PhD student of mine, Jordi de Jonge, and we have already basically gotten all the results. We can take the Hall Mhd limit, for instance, from the 2-fluid limit. We find again the Mhd limit, and we can connect with many points in literature that were previously a bit confusing to connect, at least if you come from the Mhd time. And talking about Mhd, I'd like to welcome, to warmly recommend our book, where for instance, you can find this dispersion relation and its derivation in all these details. And with that, I'd like to conclude my talk.
Thank you very much, Dr. Kippens, for a very transparent, interesting talk. And,
thank you.
And also finishing on time. So I request for the audience to ask question, if any.
Dr. Kirit Makwana, he wants to ask the question.
Yes.
Hi, Ronnie.
Hello, Kirit.
Yeah, hi. So you mentioned you are identifying alphanes slow and fast even in the 2-fluid, but like for example, the alphane relation omega equals k parallel VA, that's only in the Mhd limit where the electron mass is 0. So how is this modified in this 2-fluid description?
So the point is that, thanks Kirit for this question. So the point is that, as you know, indeed in the Mhd case, basically, all the waves, the slow, alphane and fast, are non-dispersive, okay? And so you should look at, if you see my cursor, okay, I'm trying to point you to this bottom corner of this diagram. And so there you see indeed how in that limit you have the green, the red and the blue, namely the slow, the alphane and the fast. And they are indeed in that corner. Actually, the whole description is fully consistent with relativistic magnetohydrodynamic expressions for these waves. And so in Mhd, you wouldn't have the dispersive character. By dispersive, I mean that these lines are not staying straight as you follow each and individual line. You see that, you go to a resonance or you go to another limit, basically. But in Mhd, you just have them, non-dispersive. I hope that answered your question, or another.
Yeah, thanks.
I have a question.
Yes, go ahead.
This is Ganesh here from India.
Oh, hello, hi.
Thank you for a very nice talk, as usual.
Thank you.
If we add to this formulation a tiny bit of thermal effects, what would happen to the overall phase and group diagrams?
Thank you for your question. So indeed, I should have made clear already in this slide, in fact, we have thermal effects, because in this slide, I show the S mode, which is the slow magnetoacoustic mode, okay? So that's the other thing. The point is that this is the overall structure of the dispersion relation. The reason why textbooks can work with a quadratic equation in n squared is because if you ignore the thermal effects, then all the k to the power 6 and k to the power 8 terms vanish. All those coefficients here, I didn't give you the expressions, but they basically are proportional to the pressure, and so they vanish. If you want to treat a warm ion electron plasma, you have to handle already something that is fourth order in k squared, basically. So you can no longer do these Klemov-Mullally-Allis, because now at a fixed frequency, you would have to deal with the possibility of up to 4 modes. And so that's why, again, it's better to well, look at the fact that it's just 6th order in omega squared. That's the easiest, that's just counting the waves.
I believe it would become even more complicated if you include a non-uniform magnetic field.
Well, that's another point. Thank you for that point. Thank you for the question. So indeed, here, this is the textbook treatment where we have a uniform medium, okay? And also this, this thing here is, of course, the Friedrichs diagram for a uniform medium. But in fact, in our book and in many other places, you know that even magnetohydrodynamic waves behave very intricately if you start to look at them in non-homogeneous medium. But there, it has turned out that in MHD, the slow, alphane, and fast organize the entire spectrum. And they organize where, for instance, the Rayleigh-Taylor, or where the Kelvin-Helmholtz, or where all the other, the familiar fluid instabilities are found. They are organized about this essential spectrum. So my point is, we better carry this over to a two-fluid description. This was all for basically linearization about a uniform medium, but you can do the same thing for a non-uniform medium, and you will find even more surprises, and all of this has not been done. That's the main thing. This is a new research field, I think.
For example, in TAE mode, a TAE gap would also be recovered, I guess, when you apply to...
absolutely, absolutely. Yeah.
And would it throw new light in some sense? Because TAE is a big area for MHD spectroscopy in supermax.
That's right, that's right. Yeah. So the point is that if you want to study TAE modes, you typically want to do that with an equilibrium given by a Grachavranov solution, basically. So already the equilibrium is 2D, right? And then you would have to do your linearization about that equilibrium. It's technically feasible, and it has been done in MHD, but I'm not aware that it has been done for a two-fluid description.
Thank you.
Yeah, thank you.
Let's thank you once again, Dr.
Yeah, okay.
For a nice talk. So let me now invite the next speaker, Dr. S. Krapek, Institute of Materials Physics in Space German Aerospace Center, DLR, Germany. The title of the talk is Collective Excitations in Strongly and Moderately Coupled Complex Plasmas. Dr. Krapek, did I pronounce your name correctly?
Yeah, thank you. It was correct.
Oh, thank you very much. So
Okay.
please start your talk.
Thank you for the introduction, and good morning, everybody. And first of all, I would like to thank the organizers for providing the opportunity to report this work, which is a great honor for me. And now I will share my screen. So in my talk, I'm going to go beyond the electron and ion plasma and add the dust particle into consideration. So I will be talking about wave phenomena in a complex plasma. And this is the content of my talk. I will start with introducing collective modes, then talk about dust acoustic waves, very important concept in the field. I will present some example from early research, introduce Yukawa systems, which are models of complex plasmas, and then discuss what are ways of to quantitatively describe the effect of strong coupling on dispersion relation of collective modes. And towards the end of the talk, I will briefly discuss the effect of coupling, potential softness, and spatial dimensionality on sound velocities. So, as you know, wave phenomena can be very often observed in experiments, and comparison with theoretical expectations can be used to estimate important plasma parameters such as particle charge, plasma screening length, and so on. As you also know, many effects can affect wave propagation. For example, charge variations, forces acting on the particles, plasma, in particular ion flows, various interaction mechanisms between the particles, confinement. But in this talk, I will not consider these complicated effects, but I will mostly focus on the effect of strongly coupled. That means on the effect of interparticle correlations. So these effects are investigated in theory, for instance, using different approaches such as generalized hydrodynamics, mode coupling theory, quasi-localized charge approximation, and I will be mostly dealing with quasi-localized charge approximation, and also, of course, in numerical simulations using molecular dynamic simulations. So here I present dust acoustic waves, which is very important and in fact one of the central concepts in the field. So this is a dispersion relation of a longitudinal wave that can propagate in complex plasma consisting of particles, electrons, and ions. And this is a sketch of this dispersion relation. So the main properties are that dispersion is acoustic at long wavelengths here, and therefore the mode is called dust acoustic wave. And then when the wavelength decreases and the frequency approaches the dust plasma frequency. And also here in the inset, I show the dispersion relation of the one component plasma, that is when the screening lengths go to 0 and we have particles on the immobile neutralizing background. Here the properties of this dispersion is that the frequency starts from the plasma frequency and then increases due to kinetic effects. Some examples from early plasma research. In this case, I show the results from molecular dynamic simulation by Hansen some 45 years ago, who studied dispersion relation in three-dimensional one-component plasma. And here you can see an effect that the effect of strong coupling causes the dispersion to transit from the positive dispersion, like here, when we have an increase of the frequency with wave vector, to negative dispersion, where the wave frequency decreases with wave vector. And this transition happens at approximately gamma equal to 10. And gamma is a coupling parameter. I will introduce it in a minute. Here is another example of waves, of wave dispersion in three-dimensional Yukawa fluid. Here you can see that two modes appears. One high frequency is the longitudinal mode, and this one is the transverse mode. The shown are the results from MD simulation by Ohta and Hamaguchi. And in particular, I would point out the existence of very long wavelengths for which the transverse mode cannot propagate, and this is often called Q gap for the transverse mode at long wavelengths. One more example, this is shown comparison between dispersion relations obtained from molecular dynamic simulation and quasi-localized charge approximation, again for a three-dimensional Yukawa fluid. And you can see in this case that in general, a quasi-localized charge approximation describes quite well the dispersion relation obtained from numerical simulation, but cannot describe the existence of the Q gap, that is the absence of transverse mode at very long wavelengths. So main observations so far are that strong coupling effects modify dispersion at of longitudinal waves at short and long wavelengths, and also affect, of course, the sound velocity. Transverse shear mode can exist at strong coupling and exhibit gapped dispersion relation. So, and in the rest of my talk, I will describe simple tools to quantify these effects. I start this part of the talk with a brief description of Yukawa system as a model of complex plasma. So Yukawa systems are systems of point-like particles interacting via Yukawa potential or Coulomb screened potential. So in this treatment, electrons and ions are just producing screening and are not treated explicitly. The phase state and all the properties of Yukawa systems are determined by two dimensionless parameters. Gamma parameter, which is basically the ratio of the interparticle interaction energy to the system temperature or system kinetic energy, and the screening parameter, which is the ratio of the interparticle distance to the screening length. And I should mention that phase diagram, thermodynamic and transport properties of Yukawa systems are very well understood. And in this sketch, as an example, I show you the phase diagram of Yukawa system. So showing that it can exist in fluid state, and with increase of coupling, it can crystallize into the solid phase as a BCC for smaller screening parameters or FCC for larger screening parameters. So one of the very useful ways to describe dispersion relations is a method based on frequency moments and related to quasi-crystalline and quasi-localized charge approximation. So here are the expressions for the second frequency moment of the longitudinal and transverse current correlation functions. And you see that they consist of two terms. First terms are kinetic terms, and the second terms are related to the interparticle interaction potential and radial distribution function G of R. And the potential terms are considered as approximation of the corresponding collective mode description in liquids. And this is applicable not only originally it was proposed for normal neutral liquids, and then it was developed into a theory of quasi-localized charge approximation to apply this for plasma-related systems. And why the potential terms can be considered as good approximation of the dispersion relations is excellently clarified by the derivation of Hubbard and Baby, and they called the model as quasi-crystalline approximation. And in the plasma-related context, we know this as a quasi-localized charge approximations. So the important point is that dispersion relations are expressed in terms of the pairwise interaction potential and radial distribution function. And as I mentioned, originally it was proposed as a general tool to describe collective modes in fluids. And for plasma-related systems, there is some specifics. The point is that the radial distribution function appears under the integral in the QCA or QLCA approximations, so it's not very unreasonable to assume that a simple model can be constructed which allows to describe the required integral properties. That means the model radial distribution function should not necessarily be very close to its actual shape, but it should possess properties that will describe appropriately the integrals involving this function. So, and for soft and long range potentials operating in plasma related context, the important point is that contribution from distant interactions are important. And in this range of distances, the radial distribution function exhibits small amplitude oscillations around unity. Also, a strong coupling when the repulsion is between particles is strong, the contribution from short distances is small, simply because the particles cannot approach close to each other. So effectively, a correlation hole is formed with a radial distribution function equal to 0 inside this hole. And so the simplest model which satisfies these above mentioned properties is just a stepwise radial distribution function shown in this figure. So R in this context is a free parameters, but it's not really a free parameter because we fix it by requiring that this model RDF delivers good approximation for either excess internal energy or excess pressure using energy or pressure equations from the liquid state theory. And then the advantage of such a simple model, of course, which is not relatively far from the actual radial distribution function, the advantage is that in many cases, for many potentials, the integration can be performed analytically, and then we obtain very simple explicit analytical expressions for the dispersion relations. And I will show in a minute how it works for various cases. So first example is one component plasma in 3 dimensions, and you can see that this model RDF provides you with particularly simple analytical expressions for the longitudinal and transverse dispersion relations, and they are describe the existing numerical data very accurately. The second example is that for Yukawa systems in 3 dimensions, so again, as you can see, simple explicit expressions for the dispersion relations can be derived, and they compare very favorably with the results from molecular dynamic simulations, except of course this quasi-crystalline or quasi-localized charge approximation cannot describe the existence or the Q gap in the dispersion relation for the transverse mode. But this is well-known problem with quasi-localized charge approximation, and I will talk on an approach to fix this problem in the rest of my talk. So right now I will describe a heuristic approach to improve quasi-localized charge approximation to take into account for this vanishing of transverse waves at very long wavelengths. So as I showed you, simplified QLC produce very simple expression for the transverse dispersion relation. Now we combine this with the fact that the transverse current spectrum in the generalized hydrodynamic approach has this shape, and from this we immediately see that if the peak in the transverse current spectrum exists, it's located at this frequency. So this is shifted from the frequency derived from the quasi-crystalline or quasi-localized charge approximation, and by the term which is related to relaxation time, shear relaxation time. And an important point here is that this term, second term related to relaxation time, is important only at the onset of the shear wave. That is, for sufficiently small wave vectors. So taking shear relaxation time in as a Maxwellian relaxation time, which is the ratio of the shear viscosity coefficient to the shear instantaneous shear modulus, we can estimate this relaxation time at the limit of long wavelengths, and this will give us appropriate estimation of the term. And I will show that indeed this approach works quite well. But first I need the viscosity coefficient for Yukawa system. And viscosity coefficient in fact has a universal dependence of on the coupling parameter in the strongly coupled regime, and I take this estimate for the calculation, which will be presented on the next slide. Here is the results for the three-dimensional one-component plasma, and the curve corresponds to the approach that I just discussed, and you see that it works quite well. Next example is comparison with numerical data related to three-dimensional Yukawa fluids, and again you can see that Q-gap in the dispersion relation of transverse waves is very well reproduced, and also its position is very reasonable compared to the simulation results. So the approach goes beyond the complex plasma or plasma-related systems, and as an example, I show how it works for liquid metals using the available the data reported by Hosokawa and others. And you can see again that the prediction regarding the existence of the gap in the transverse dispersion relations are well consistent with the experimental results. So overall agreement is satisfactory. Next point is what governs the dispersion relation at weak and moderate coupling. So far we were concentrated on the regime of strong coupling, but now I will go to the regime where coupling is smaller, and when the kinetic effects can be comparable to the effect related to the interparticle interaction. So in this respect, it's useful to recognize that we can express the transverse and longitudinal wave dispersion in terms using the generalized bulk and shear instantaneous elastic moduli like this. So that in the limit of long wavelengths, we have familiar relation between bulk modulus, shear modulus, and longitudinal modulus. And at the next step, we recognize that shear mode can be only support at sufficiently strong coupling. So at weak and moderate coupling, shear modulus, shear mode, transverse mode disappears. So, and then it's tempting to assume that when the shear mode disappears, the shear modulus, generalized shear modulus, is essentially zero, and then the dispersion relation of the longitudinal wave is expressed in terms of the generalized bulk modulus. So the hypothesis here is that when coupling becomes weak, the dispersion of the longitudinal mode is provided by the sum of the excess bulk modulus and Bohm gross kinetic term. And indeed, molecular dynamic simulations demonstrate that this is the case. So it's probably not very easy to see here, but comparison shows that indeed the combination of excess generalized modulus plus Bohm gross terms is the best, the corresponding curve is in the best agreement with the simulation results that we have obtained. And to conclude my talk, I will make two statements that might be useful. So first statement is about how the sound velocity depends on coupling and screening. So if we take the weak coupling or conventional dust acoustic velocity as a scale, the question is how the sound velocity in will be changed due to effect of strong couplings. And the situation is shown on these two figures. First of all, we see that deep in the fluid regime, the ratio of the actual sound velocity to this dust acoustic scale is practically constant. So it doesn't depend very much on gamma, so only weak dependence on gamma, but the dependence of the screen parameter is relatively strong. And you can see that the ratio is close to unity in the close to the one component plasma limit when kappa is equal to 1 or less, but then the ratio drops considerably with kappa. So strong coupling reduce the sound velocity, and the effect is particularly pronounceable for large kappa, so for large screen parameters. And then the last point is the sound velocity versus spatial dimensionality. So at strong coupling, the sound velocity scale can be expressed in terms of the like this, and the actual sound velocity then is a product of this scale multiplied by the function of the screen parameter, and as you can see from this figure, the function diverges as kappa goes to 0 and behaves differently for different dimensionality. Here, the results are shown for 3-dimensional red curve, 2-dimensional blue curve, and 1-dimensional situation. But with increase of kappa, the effect of dimensionality virtually disappear, and the function approach the approximation of one-dimensional lattice with nearest neighbor interactions. And so this is interesting observation that for sufficiently strong screen, that is for sufficiently steep potential, the dimensionality doesn't play a role anymore, and sound velocity is essentially properly normalized, of course, is essentially the same for different dimensionalities. So at this point, I came to my conclusions. So I summarized recent progress in understanding and describing of collective modes in complex plasmas, discussed some simple analytic dispersion relations, talked about gap dispersion relation of the transverse mode, discussed dispersion relation at weak and moderate coupling, and the last two slides were devoted to dependence of sound velocity on coupling, screening, and spatial dimensionalities. And I would like to thank you for your attention and acknowledge the contribution of my colleagues to this work. So thank you.
Thank you very much, Dr. Kapil, for good talk. Any question from the audience?
Pratiksha, you may ask the question.
Did you, sir?
Yes, speak.
Thank you, sir, for the wonderful talk. I'd like to ask you a question. In case of longitudinal negative dispersion, I mean omega decreases with increasing K. So may I know what is the physical significance of negative dispersion? Is it a strong coupling effect, or it can be weak coupling regime also?
Unfortunately, I couldn't hear the question. Can you repeat it, please?
Not very clear.
Now, her question is, what does negative dispersion signify physically? Also, why at certain wave vectors, wave mode is not excited?
I understand that it's about negative dispersion, right?
Yeah, about
Yes.
negative
So,
dispersion.
yeah. So you can see here that for weak coupling, the dispersion is positive, and the frequency bends upward due to kinetic effects, basically due to bomb gross term. But when coupling becomes stronger, it provides negative contribution to the dispersion relation, and at some point, the frequencies start to decrease with kappa. So the effect is just the same. For the same reason, the sound velocity in Yukawa systems decreases with increase of interparticle coupling with interparticle correlations. So it produces a negative effect on the frequency.
Okay, so it looks, so thank you once again, Dr. Kapil, for interesting talk. Now I request the speakers in the oral presentation. So the first talk is from Dr. K. Makwana, Indian Institute of Technology, Hyderabad. The title is Properties of Magnetohydrodynamic Modes in Compressively Driven Plasma Turbulence. Dr. Makwana, are you there?
Yes, I am here. Can you hear me?
Yes, very well. So
Okay.
Please take note of time. So we should finish on time. People might be hungry.
Yes.
Okay. Thank you.
Okay, I'll share my screen.
Yes.
Okay, just a minute.
Kirit, please on your video also so that participants can see you.
Okay, I think there is some, I have to quit. I'll have to exit and come back in. Just a minute. Sorry.
Okay, no problem.
Mhm. Maybe we can take the next talk and then after this, Dr. Prajapati, what do you think? Is going to take longer time?
No, he is connected, I think.
Okay.
Yeah.
Okay, he's
Okay, sorry for the trouble.
no
There is some
problem.
issue.
Please start. Yeah, okay.
Okay, I just share my screen. Okay, so I hope you can see my slide.
Yeah, we can see your slide.
Okay, so I am Kirit Makwana. I am going to talk about compressively driven plasma turbulence. I recently joined IIT Hyderabad. Before this, I was at DESI. And this work that I am presenting is work that is done in collaboration with Professor Jan at DESI Zeuthen. And before that, I was a postdoc with Professor Keppens, who just now gave a talk. So actually, his talk was a good introduction for this kind of work. I am analyzing Mhd modes. And he already showed that you get different modes when you solve for a plasma dispersion relation. So if you solve for the Mhd equations, you will get three modes: alpha wave, slow magnetosonic wave, and the fast magnetosonic wave. So these can be thought of in this, in terms of Fourier space, you plot it in terms of wave vector and omega. So if you look at the middle figure, it shows three eigenvectors. So this Kasai is basically the displacement vector of that mode. And Kasai A is the displacement vector for the alpha mode, Kasai S for the slow, and Kasai F for the fast. And you can see that they are different. So the alpha mode has a displacement which is perpendicular to your wave vector and your background magnetic field. In the figure on the right hand side, you will see that the displacement vectors for the slow and the fast modes are in the plane of the wave vector and the magnetic field. And they can change depending on what your plasma beta is. So alpha mode is an incompressible mode because its displacement is perpendicular to k vector, whereas the slow and the fast are compressible modes because their displacement has a component along the wave vector. So when we talk of turbulence, a lot of studies have been done for what is called as alpha mode turbulence. In analyzing this kind of turbulence, what people assume is you have wave packets which are made up of alpha waves. So in this cartoon, you can see a magnetic field line. And on top of this magnetic field line, there are some fluctuations. So these are basically alpha wave packets. And these wave packets have some characteristic length scale. Some parallel length scale, which is the length scale in the direction of the mean field, and perpendicular length scale, which is perpendicular to the mean field. And theoretically, people have identified over many decades of work that there will be two regimes of turbulence if we consider alpha turbulence. So before I go further, I should mention that in turbulence, you might be aware that you have nonlinear interactions and energy cascades from large scales to small scales. So you have big eddies interacting and producing smaller eddies, and these smaller eddies interact and produce further smaller eddies and so on. So that's a turbulent cascade. And in MHD, you can show by using weak turbulence theory. So on the left-hand side, I am showing some relations that weak turbulence has to satisfy. And basically, if you look at these equations, what you will find is that in weak turbulence, you get three wave interactions in which one of the wave vector has a k parallel equal to 0. Physically, what this means is that you will not cascade energy to smaller scales in the parallel direction. Which means in weak turbulence, if you have a wave packet with L parallel and L perp, L parallel will not decrease, only L perp will decrease because the cascade will be anisotropic and it will cascade only in the perpendicular direction, perpendicular to the magnetic field. If you go to strong turbulence, then you will reach a stage called as critical balance conjecture made by Goldreich and Sridhar. And this states that there is some balance between the nonlinear time scale and the linear time scale. And again, you can see this, it's not difficult. It can be shown that it will satisfy this relation, which is shown at the right bottom. K parallel should go as K perp raised to 2/3. So this is the Goldreich-Schrieder conjecture. Now all this is theory. What are we trying to do? First is, does this theory really work? We want to verify that using Mhd simulations. Second question is, what about the slow and the fast mode? People are always talking about alpha modes and what is their spectrum. But the spectrum of the slow and fast modes is very poorly understood. So numerical studies are also limited and they do not show clearly. This is one of an earlier study by some people, and here you can see a spectrum of energy spectrum as a function of wave number. And the three colors are the three modes. So you can see alpha in blue, slow in red, and fast in gray. And this is typical of what has been studied till now. People generally, what you get is, you get alpha and slow, which are comparable, and the fast modes is very weak compared to the alpha and the slow mode. So we've also wanted to study whether we can have more fast modes in simulations. So what we did was, we did Mhd simulations of Mhd turbulence. And for this, what we do is, it's readily available in Mhd codes. You can add a force in your momentum equation, which is the first equation. So you take your momentum equation and you add a forcing term. And what we did is, we took a specific kind of forcing term, which is called as OU forcing. And it is basically, a force itself is governed by a stochastic equation, which is shown in the second equation. And the nice thing about this forcing is that you can split the forcing into solenoidal and compressive parts. So you can project your forcing operator into an incompressible solenoidal part and a compressible divergent part. After doing the simulations, we decomposed the data into the three Mhd modes, and we looked at the energy distribution in these three modes. So the figure on the right bottom, it shows the three modes in three colors. Blue is alpha, green is slow, and red is fast. The simulations on the left are solenoidally driven. The simulations on the right-hand side are compressively driven. And you can clearly see that when you drive simulations compressively, you get a large fraction of fast modes. But this is something that was not observed before. And fast modes were always thought to be very negligible. But apparently, if you drive them compressively, then the fast modes form a large part of your turbulence. That is important. That is the first important point. Then we looked at the energy spectrum to understand whether that cascade theory is correct or not. So this is a two-dimensional energy spectrum. The horizontal axis is K perp, the vertical axis is K parallel, and the color is the power. And there are four simulations starting from low MA. So the top left MA is 0.24. Then we are increasing the alpha and Mach number and slowly reaching Mach number of 1. And we can clearly see a transition from weak turbulence to strong turbulence, because in the top left, you can see the energy. It starts from low K parallel and K perp, and it continues to go towards larger K perp, but it does not go in the vertical direction, which means the energy is not cascading in the parallel direction. It's only cascading in the perpendicular direction, which is the characteristic of weak turbulence. If you go to MA equal to 1, we see that the energy still cascades more in the perpendicular direction, but there is also some energy going to higher K parallel, which is in the bottom right figure. So there is a transition. So we are able to verify there is a weak regime of turbulence and a strong regime of turbulence. And this transition depends on the alphanic Mach number. We also verified the spectrum. I'll not go much into detail here. The figure on the right is a theoretical prediction for what the spectrum should look like. So when you start at small wave numbers on the left, you are in the weak regime. And as you go to larger wave numbers on the right, you go to a strong regime. And we verified this at low MA. The figure on the left, the blue curve is the alpha mode. It is showing a K perp to the -1 spectrum, which is the spectrum predicted on the left-hand side. The bottom figure, the spectrum is K to the -3/2, which is the spectrum predicted on the right-hand side of the figure. So the spectrum is correct as per the theoretical predictions. Then some more things which we verified is the transition scale. The transition scale between the weak and the strong, it is theoretically predicted to scale as MA square. So basically this expression which you see, lambda CB is the transition scale. It should behave as L injection times MA square. We estimated this transition scale from the figure on the left. The figure on the left is calculated from the structure functions, which is showing the correlation between the parallel length scale versus the perpendicular length scale. So it's L parallel versus L perp. And you can see that at small ma, which is the blue color, the L parallel is constant and L perp is decreasing. Whereas when you go to high ma, you start following the Goldreich-Schrieder slope, which is the 2/3 slope, which is shown by the red dotted curve. And from this, we could derive the transition scale as a function of ma, which is shown on the right-hand side figure. And this transition scale goes as MA square. So this is another verification of the theoretical prediction. So the blue line is an MA square reference line, and the different points on the right-hand side are the transition scale measured from different simulations. And you can see that roughly, it's not very perfect, but it is roughly following the MA square reference line. The different colors are for different types of simulations. So that kind of verifies this relation. And then going to fast modes, we looked at the energy spectrum of the fast modes that is shown on the left-hand side. And you can see clearly that the cascade is very different from alpha mode. The cascade is very isotropic. Isotropic means it is going equally in K parallel and K perp directions. So this is interesting. It's very different from alpha. And this is something that is verified from the structure functions also, which is shown on the right-hand side. So that is plotting L parallel versus L perp, and you can see it clearly follows L parallel equal to L perp slope, which means the structures are such that they have equal lengths in parallel and perpendicular directions. So it's isotropic. And based on this, what we found is that there is something which was not expected. This is the spectrum of the modes versus K parallel. And the green is the fast mode, the yellow is the slow, and the blue is the alpha. And you can see on the right-hand side figure, there is a turbulence of weak alpha modes. So when the alpha cascade is weak, the energy does not go to higher Kz. Whereas because the fast mode is isotropic, the fast mode energy goes to higher Kz and its energy becomes more than the alpha mode. So this was something interesting for us because typically we always ignore the fast mode. But here it shows that in the case of weak alpha turbulence, you can have fast mode which can be dominating at high K parallel. And the reason this is important is because at high K parallel, you have a lot of scattering mechanisms which depend on fluctuations at high K parallel. For example, in the last line, you can see the resonance, gyro resonance equation. It depends on Kz. And at high Kz, if you have fast modes, then you can have more scattering. A colleague of mine used this.
Your time is almost finished.
Okay,
So
this is the last slide. This is the last slide.
Okay,
so using this, colleague of mine was able to identify these modes in interstellar medium turbulence. So that is shown on the right-hand side figure. So the red regions are regions where we believe there is fast modes, and the green regions are regions where we believe there is alpha mode turbulence. So yeah, that's my conclusions. And this work is published in PRX this year, so you can find it there. And the new things we found is that compressive driving leads to more proportion of fast modes, and these fast modes have very different properties from alpha modes. So it gives rise to different kind of turbulence. So thank you.
thanks, Dr. Makwana. So,
Sir, sorry to interrupt you. There is one question written by Ronnie Kepan in chat box.
Yeah.
Can you clarify if the simulations are ideal DNS MSD simulations, or do you have the
Visco resistive. I made a typo.
Oh, sorry. You are there.
Yeah.
phase.
So the question was indeed whether it's ideal MHD, and hence you have some sort of numerical dissipation at ultimately, or do
it's
you have
ideal
disco
MHD.
resistive?
It's ideal MHD, so it's just numerical dissipation.
Okay, okay.
Yeah.
And can you clarify, like if you were to repeat this with some sort of resistive effects, to what length scales would it extend? Like where would the dissipation scale be in your spectra? Much to the right, I suppose, right?
It would be much to the right. It will be much to the right. So already this is quite, the numerical dissipation is quite strong. So you can see that the spectrum is getting cut off at more like, so basically 1 year is 256, and so it's going to up to like some 50 or 60 points or something scaling. So it is getting cut off. If we add resistivity, the cutoff will shift to the left hand side, but it should not change the qualitative results of these different modes.
Yeah, no, I think it's very good that you now identify where the more isotropic fast ones come in. I mean, that would be great. That's great. Thank you.
Okay. Thank you, Dr.
Hi.
The next speaker, Dr. M.K. Shukla from Jawaharlal Nehru College, Pasighat, Andhra Pradesh. The title of the talk is Thermodynamics of Yukawa gas, Simulation and Application. Dr. Shukla, are you there?
Yes, sir, I am here and I can hear you.
Please finish on time. Okay, you can start and welcome.
Thank you very much, sir. First of all, I would like to thank the organizers for giving me the opportunity for presenting my work. Today, I'm going to talk about the thermodynamics of Yukawa gas. I will also talk about the simulation and its application. And this work has been done in the collaboration with Professor Avinash Khare, Professor Ganesh, and my best friend, Rupak Mukherjee. So let me just show you what are the outlines of the talk. Can you see my screen?
Yes, we can see your screen. Very nice. Okay.
So here are the outlines. First of all, I will briefly discuss the introduction and then give you the equation of state for the Yukawa gas. And I will also discuss the free expansion of Yukawa gas, followed by the equilibrium structure of self-gravitating charged dust clouds. So we know that plasma is the collection of electrons.
Your voice is little down, so can you focus on my phone? Okay.
One sec, sir.
Okay.
Is it audible now? Yes.
Yeah, now it was fine. Yeah.
Okay, sure, sir. So plasma is collection of electrons and ions, and if we add some grains of some kind of 10 to the power minus 10 grams and of size micrometers or sub-micrometers, then because the electron's mass is much lighter than that of the ion's mass, they are first to reach the dust particles, and this makes the dust negatively charged, and the amount of the charge which can dust acquire is of the order of 10 to the power 4 electronic charge. So this is how the dust is charged, and this kind of charge, when present in the electron ion plasma, this can be modeled using the Yukawa model. As you can see, mathematically, this is the equations which give you the interaction. Here, electrons and ions are assumed to be Maxwellian, and we write the Poisson equation for the system, and we get the Yukawa potential for the dust grains. Next, we come to the weakly and strongly coupled plasmas. We know there are two parameters which can perfectly define the thermodynamic state of dusty plasmas. One is the gamma, which is also called the Coulomb coupling parameter, which is given by this expression. And another one is the screening parameter, which is the ratio of interparticle spacing to the Debye length. And the dust-dust correlation is measured by this factor, the gamma star or gamma asterisk, which is given by gamma times exponential of the screening length. So when the gamma star is much less than 1, the system is classified as weakly coupled system, and such system can be idealized as ideal gas. Whereas when gamma is of the order of 1, this is said to be the moderately coupled system, and they can be realized like the real gases. And when this system, when the gamma star is much greater than 1, the system is strongly coupled and it behaves like the solid state matter. So in this way, by varying this gamma and kappa, we can study the whole phases of these dusty plasmas, right from the ideal gas to the solid state regime. So this is now the next topic which I am going to emphasize much more, the equation of state of Yukawa gas. The reference of this topic can be found in this paper. So let me start why we are going to study the ideal gas, the equation of state. We know that the ideal gas, the pressure is given by the ideal gas equation, PV equals to nRT. I'm sorry. And in this ideal gas, we also can see that the pressure only comes from the kinetic part because there is no interaction at all. Surprisingly, the same thing is seen in the electron ion normal plasmas also. However, the electron ion plasma has long range interaction. Still, the equation of state is similar to the ideal gas equation. And the reason behind that is that the electron in electron ion plasmas, the intermolecular distances is much large, so that the interactions is screened significantly, and the pressure is given by the kinetic pressure only. However, in dusty plasmas, since the charge on the dust is much bigger, so the interactions cannot be neglected and the system becomes complicated. Therefore, the pressure of the Yukawa system is expected to be different from that of the ideal gas pressure or the electron ion plasma pressure. So let us come to the other things. This is not that we are the first who is gonna explore about the equation of state. There has been previous studies about this. I am giving some analytical references as well as simulation references. However, why we are gonna revisit these equations? Because all these references assume that the electron ion plasma and the dust occupy the same volume in their model. And due to this, there comes many anomalies, which I'm going to discuss in the next slide. For example, here I have discussed three experimental papers where it has been seen that the measured pressure is not consistent with that of the theories or the models which have been given earlier. And the crucial point which is missed in this in the above models or the previous models is, as I said, the confinement of the dust. Because in real experiment, what happens that the dust is confined in a smaller volume compared to the electron ion plasma volume, and the dust volume can be manipulated differently, or you can say independently from the plasma volume. So taking into account this confinement effect, Avinash has proposed a model which takes into account the confinement effect, and he analytically gave some expression for the pressure of this confined dusty plasmas. So I am going to verify them numerically using MD simulations. So here I am again showing you what the previous models show. In previous models, generally the square box of volume V is taken, where the plasma is also occupied and dust is also occupied in the same volume, and then periodic boundary conditions are used. And once again, this is to be noted that the dust and the plasma are occupying the same volume. Therefore, there are no confinement effects. Whereas the real experimental conditions are that the plasma is filled in volume V, then dust is filled in another volume Vd, and this dust is confined by the means of external fields in a smaller volume. And this situation is analogous to an electrostatic bowl in which the potential inside the bowl is negative, whereas the outside the bowl, the potential is 0. And taking into account this model, Avinash gave the expression for the electrostatic pressure, which has the quadratic dependence on the number density. So what I am going to do is to numerically check whether this expression is all right or not. So my work is here. I am presenting here the verification of this model. Yes. Is there some question? Okay, so here are the simulation details. This is the interaction energy. This is the force on ith particle. And it is important to note here that I have normalized my units in terms of these units, means my lengths are normalized with the Debye length. My time is normalized with the omega 0, where omega 0 has been given by this expression. Energy is normalized by qd square upon 4 pi epsilon naught lambda d, and so on. You can see on the screen. And in my units, the screening parameters is this, and the gamma, which is the Coulomb coupling parameter, becomes 1 upon kappa times temperature of the normalized temperature, in fact. So what I did for the equation of state, you can do two ways. You can perform this experiment in two ways. First, what you can do that take some gas, keep its temperature constant, and increase its volume. So the same thing I have done here, that I have taken the number of particles, suppose n number of particles, and then I am varying its volume and keeping the number of particles same, and the whole thing is on constant temperature. Also the temperature, the pressure is calculated using the virial expression, which has the formula is shown here. And to take into account the confinement effects, I have applied the perfectly boundary conditions, perfectly reflecting boundary conditions. So here are the results. First of all, inspired by these results, the earlier analytical results, I have fitted my result in these parameters, where you can see that the first expression here is the kinetic pressure, which has the first order dependence on number density, and the second term has the second order dependence on number density. Therefore, I have fitted my results in this order: PD equals to alpha times ND plus beta times ND to the power gamma. So alpha, beta, and gamma are my free parameters, which are to be fixed by the simulation. Also, I have taken three temperatures: 0.20, 0.1, and 0.5, and number density has been varied in such a way that kappa remains in the weakly coupled regime only, so that we are talking about only the Yukawa gas, not the Yukawa liquid or Yukawa solid. So here are the results for different temperature, and here is the expression for everything is shown. This is another result for number of particles taking 6,000. And here I summarize all the results in the same equation and carefully analyze what are the different factors. As you can see here, this is TD, and alpha comes out to be exactly equals to the TD in all the three temperature parameters. So it is immediately comes to us that alpha is, that alpha is equals to the dust temperature, while gamma is close to 2. You can see all in the these parameters in the three results. So broadly we can see that the expression is of this nature: PD equals to ND TD, because alpha equals to TD, and the exponent of ND is 2, while beta is not fixed. For example, for TD equals to 0.2, it is 4.1, then it is 3.6 and 3.4. So beta is constant, which varies from 3.4 to 4.1. And it is to be noted that beta is the factor which takes into account the effect of coupling. So if your density is much more, or density is less, or temperature is less or more, so beta is implicitly dependent upon gamma also, which we have to still explore. So in conclusion, the electrostatic pressure has been obtained, and this is also been seen experimentally in the experiments of Fishers and all in 2013, where they measured this energy density of dusty plasma in absence of any kind of wave or turbulence, and the scaling has been found to be exactly same as predicted by Avinash and as predicted by my simulations, where the exponent goes as the square of the density. So I can make a statement that the Yukawa gas, like in ideal gas, the pressure goes as 1 over V, but in Yukawa gas, instead of, in spite of having one term going over 1 over V, we have another term which goes as 1 over V square. And this pressure, the second term which comes from the confinement effect, this is many times termed as electrostatic pressure because this comes from the electrostatic fields contribution. So one thing also I would like to mention here, that though we have provided this simulation for the weakly coupled system, but there are other evidences where this scaling has been found to exist even in the strongly coupled system. So this is another point where we have to explore much for the strongly coupled system, that what will be the closed form of the equation of state. For example, here you can see in this slide, in the lower region, of course, the density plasma is, or the Yukawa system is a strongly coupled regime. Still, it follows the linear density profile, which means if we calculate it back, it means the pressure goes as square of the number density here. Another evidence is from this Dojudar
Dr.
paper.
Supta, your time is over already, so please stop now.
Okay, okay. Thank you, sir. So I had many things to explore, sir, but yeah,
Okay.
some questions, sir? Yes, sir.
Yeah, any question? Thank you, Dr. Supta.
So I have a question. This is Ganesh here. A comment.
Yes, sir. Yes.
Instead of using this perfectly reflecting walls, Manish,
Yes, sir.
if you actually apply external potential,
Right.
like a half kx square or a half, which has not a very geometrically straight confining thing,
Right.
will it change some results here?
No, sir.
What
The
is your
scaling of the the scaling of the electrostatic pressure is still will be the same, because the one slide where I wanted to show the anomaly, there the simulation is applied in the same way which you are talking about by applying some confinement potential. Yes, sir.
Okay. Okay.
However,
Thank
the
you.
term beta changes, sir.
That's fine. I expected
Yeah.
that, but I was thinking about n square.
No, sir. That is perfectly fine.
All right. Thank you.
Okay, sir.
So it looks, so we thank all the speakers of this session and close this session. Over to Dr. Prajapati.
Thank you.
Yes.
Yes, sir. Thank you. Thank you very much, sir, for chairing this
Thank you.
section and taking
Yeah,
this
thank you
painful
very
talk.
much.
I hope that all will be hungry. So let us will meet again at 2:55 p.m. IST. And there are so many interesting talks by Professor Michael Bonich, Professor R.K. Shajlani, NPS Seni, C.H. Rosina, Pankaj Sharma, R.K. Mukherjee, and Yashika Ghai from USA. So let us meet again in the second session at 2:55, so that we will start at 3 p.m. So please have a lunch at your home or office, and then we will meet again. Thank you very much.
Okay, it was very nice. Thank you.
Thank you.
Okay, bye.